Okay, any questions after our class from last time? Just realized, did I roll up the screen last time? I didn't, or why was the screen down? I never saw that before. So I used the Blackboard. Huh. Anyway, any questions about what we talked on the white Blackboard yesterday, on Tuesday? So we continued talking about dynamic programming, and we started a new example which considered finding optimal search trees to do a binary search. We wanted to translate text from one language to the other. And so we decided to come up with a dictionary where we store all the, I think, English words and map them to the corresponding translation in French. And then we said that not all the words might have a direct translation. So we accounted for those with these placeholders. We came up with these trees that modeled such a dictionary. Maybe I'll show you the one from the other lecture, how they looked like. It was this. We had something similar on the Blackboard. And so this is where we ended and said that an optimal search tree that contains elements I through k will have some root kr that lies between I and j. So we have to pick one of these elements as root, kr, and then we compute the optimal subtree with all elements to the left of kr, so from I to kr minus 1, and the optimal subtree that contains all elements to the right of kr, meaning all elements kr plus through j. And then we said, okay, if we have computed these optimal subtrees that contain, let's say, ki through kr minus 1, so the left subtree, and once I plug in this subtree in my actual tree under root kr, then the depth of all these nodes within that left subtree will increase by 1. And that's why the total cost of the tree with root kr will increase by what we called wij. So wij models this increase in our cost of once we plug in the subtree, in this case ij, under a new root in a large tree. And so based on this, we can now model the entire cost function of our optimal tree. So based on this, Cij, the optimal cost of our search tree containing elements I through j, can be phrased as follows. So Cij will be equal to, well, we said we have the root. Let me copy this over. Based on this figure here, I know that say Cij, so the cost of this tree will be equal to PR. So this is the probability or the frequency with which we observe keyword KR. And KR is the root, so the cost of looking up KR is exactly 1 because it's just one node that we have to consider. So that's why it's 1 times PR. Then we have the costs for the left subtree. The left subtree has cost, well, optimal costs C I r minus 1. So this is the optimal tree containing elements I through r minus 1. Now plus W I r minus 1. This is the extra cost that the left tree contributes once we plug it in under KR. And the same is true for the right subtree. You have to pay C, so the optimal cost for a tree containing elements R plus 1 through J, plus W R plus 1 J. So this is the optimal cost that we want to compute, Cij, based on subproblems Ci r minus 1 and C r plus 1J. And now if you consider these three terms, if you consider the left W, so this W contains by definition all keys to the left of R and the placeholders. This contains all the keys and placeholders to the right of R, and this is R. So basically, if I sum up these three, I will just get Wij, all the elements, all the P's and all the Q's from I to J. So I don't have to make this distinction. Since I take everything to the left, and I take everything to the right, and I take the middle element also, it's just the whole thing basically. So it's Wij. So this is the same as Wij. So this is obtained, I just indicate this here, by summing up this term and this term and this term. And the rest remains. So we still have the other terms, namely Ci R minus 1 plus C R plus 1 J. So this is the cost of the optimal tree containing elements I through J if we take root KR. But of course, we don't know if KR is the right choice. So we have to try all of them and then basically take the one that is the best. Let me write this down. I'm going to pick the optimal root as follows. We'll say that Cij equal to, will be two cases, but there's only one interesting case. Namely, by applying this equation here. So this is the cost if you pick roots R. We're going to try all roots that lie within I and J. So any elements between I and J can be our root. We pick it as our root and then define this as the resulting cost. And then we simply take the minimum over all these roots. So whichever root gives us the best tree, that's the one that we're picking. So this is equal to the minimum over we're minimizing over all R between I and J. And for every R, we compute exactly what we have described before. This is just a formula here on top. So it's I R minus 1 plus C of R plus 1 J plus our extra offset IJ, Wij. So this is the heart of this. We just try all the roots, compute the costs exactly according to this formula, and then just take the cheapest one, and this will be our optimal tree. Now, this is true if, in the more interesting case, if J is greater or equal than 1, J greater or equal than I, so that we have an interval from I to J. But we also said that we have these boundary cases where we might end up with a tree that doesn't contain any real key, but only a placeholder. And we modeled this by phrasing this as Ci I minus 1. So if J is equal to I minus 1, so meaning that we have Ci I minus 1 here, then the tree will simply contain only the one placeholder Q I minus 1. So this is the cost of the subtree that contains only this one placeholder. So this is we're describing now this relationship through a recursion, and now the question is, should we solve this with a dynamic program or not? We already have argued about optimal substructure last time. We said that if we can sort of cut out a piece or a subtree of a tree and plug in a better one, we would get sort of an overall better tree. So by that argument, we have optimal substructure. And the second thing we need for a dynamic program is lots of overlapping subproblems. So let's see if this is also the case in this particular problem. And for this, it was useful in the past to draw a so-called subproblem graph. Let's do this now. Remember, a subproblem graph was just having a node for every subproblem, and the edges indicated which subproblems depend on which. And so if you, for example, look at subproblem 1.5, so C1.5, meaning we want to find the optimal tree containing keys 1 through 5, so 1, 2, 3, 4, 5. Then, according to our equation up here, we have to try all the roots between 1 and 5. So we pick 1 as the root and compute the optimal subtree. If we do that, if we pick 1 as our root, then our left subproblem that is sort of left to compute is C10. So this is one of these boundary cases. This corresponds to this case, this case. So here J is J equal I minus 1. But it doesn't matter at this point. So at this point, we're only concerned with the structure of the subproblem graph. So if we pick root 1, we have one subproblem that we have to solve on the left, which is C10. And the right subproblem will contain all elements from 2 to 5, because we have picked 1 as our root. So we have to solve on the right problem C25. So this would be C25. Okay, I could have also picked, and I will also pick root 2, so element 2 as our root, and then my left subproblem will be C11, and my right subproblem will be C35. And I could have picked also root 3 or element 3 as my root, then my left subproblem would be C12, and my right subproblem would be C45. I think you see the pattern. And now the crucial thing is, if you look at the subproblem graph, these are edges indicating dependencies between these subproblems. And these arrows indicated whenever I want to compute C15, I must have computed already C10, C11, C12, and so on. And now if you look, for example, at subproblem C35, so computing the optimal tree for elements 3, 4, and 5. This occurred now when I picked root 2 in interval 1, 5. But also if I would pick root, for example, 6 in interval 3, 7, then I would also have to consider 3, 5 as my left subtree. Or if I picked root 10 in an interval 3, 15, then, sorry, did I say root? No, I mean, it has to be root 6, sorry. It has to be root 6. So if you pick root 6 in any interval that goes from 3 to whatever, to some j, then you will end up with one subproblem that is C35. So for all these problems, you would have to recompute C35. And the same is true, of course, for other subproblems. So in other words, these subproblems will occur many, many times. And many other problems will depend on this one particular subproblem. So we will have to recompute this subproblem many times. If we implement this equation here, this one here, if we do this in a direct recursive way, this would be highly inefficient because you have to recompute these subproblems over and over. And that's how we want to phrase this rather as a dynamic programming model where we build up the solution bottom up instead of top down, such that we avoid recomputing the subproblems multiple times. So let's try to do that. Let's try to come up with a dynamic programming formulation for this problem. And so we will use 3 different tables for computing such a optimal cost of a binary search tree. The first and most central is, of course, C. So Cij is the central are the central values that you want to store. And we do this in a table that we also call C. So we store the Cij or C whatever, these 2 parameters values in a table that we also call C. And the two dimensions run from, and this looks a bit weird, from 1 through n+1 in the first dimension, and they run from 0 to n in the second dimension. And this is only, so we have these extra rows n+1 and the extra column 0 because of these boundary cases where j is equal to I-1, where we have this leftmost subtree that only contains q I-1, or the rightmost subtree that only contains qi. And then, so what we have not discussed so far is how do we actually get the tree? So far, we only talked about how to compute the C's, how do we get the optimal scores for our subtree. But in the end, we're interested in the tree itself. And for that, we have to keep track of some extra values while computing these CIG values. And we do this in a table that we call simply root. In the root table, we will remember basically every time we have to pick this element here. So whenever we have tried all the roots and we pick the best one, we will remember which root we picked, because this will help us later, as you will see, to reconstruct the actual tree. This is in a spirit similar to the backtracking that we did in the edit distance. We always had to remember which optimal choice we made in every entry of this table. And then we use these pointers basically after computing this entire matrix to reconstruct the alignment. And similarly, you will see that we can use this extra information of all these roots that we pick to reconstruct backwards, so to speak, the entire tree, the optimal tree. So we keep track of the root nodes. Again, in a table that we call root. And for the root, we have more naturally appearing ranges of 1 through n, and 1 plus 1, and 1 through n. So in both dimensions, we go from 1 through n only, because there's no such thing as a root between I and I-1. You only need to know the root that we picked for a certain range of elements from I to j, for j greater or equal than I. And the third thing that we want to store for sort of practical reasons is an array W. So this will be we will sort of shortcut the computation of these values. Here, these ones. So we defined those. We still have this here now. The Wij's are simply the sum over all P's and J's within I and J, this range Ij. And so instead of computing Wij every time from scratch, which would require j minus I or theta of j minus I many additions, we compute one Wij based on Wij j minus 1. So just on the leftmost. But I'll show you this later. So for this, we need to keep track of some extra information in an array W. So and this is because we don't want to recompute W every time. Therefore, we have an array W. And here the index range is the same as for C, because we again have these base cases that have j equal to I minus 1. So we again go from 1 through n plus 1 in the first dimension, and from 0 to n in the second dimension. And I'll show you how to compute this in the overall description of the algorithm. But this is really just to save us some space, some time while computing these Wij entries. So let's summarize all our observations and all the equations that we came up with now in one description of the overall algorithm that we will call optimal BST. So optimal BST gets as input our values P. So these are all the probabilities of our keys, P1 through Pn. I'm just writing here P as a vector. So think of also Q as a vector. Q contains all the probabilities from placeholders, from these dummy nodes. So we have Q from Q0 through Qn. And we need to know how many keys we have. And we have n in this example or this description. So the first thing, and this is very common for dynamic programs, is that we have to initialize our structures, and in particular C and W. We have to initialize the base case, similar to the edit distance, where we initialize sort of the first column and the first row to sort of the values of aligning an empty string to some substring. Similarly, we have to align these base case or initialize these base cases, C and W. And we do this in the following for loop. So we go from I equal 1 to n plus 1. And then we can set Ci I minus 1. These are the base cases that go from I to I minus 1. So it's not really, it's an empty range of keys, but it contains this one dummy node, Qi minus 1 by convention. So this is Qi minus 1. And we do the same for the W's. Wi minus 1 is equal to Qi minus 1. That's sort of the initialization. It's not very interesting for us. It gets more interesting now when we really consider how we traverse all these subproblems in our subproblem graph from bottom to up to top. And we have to make sure that whenever we want to compute some Cij, that we have computed all these subproblems Cij that occur once you pick one of these elements as the root. And one way to do this is to realize that whenever you are going from some element, pointer also. Oh yeah. So whenever I compute the Cij, I have to make sure that I have computed all these subproblems, C I R minus 1 and CR plus 1 to all the way to Cj. And all these subproblems have a shorter interval, right? So if you compute Cij, whenever you pick a root, all the subtrees will have sort of a subrange of your initial range. And that's why we try to traverse all these subproblems basically by the size of this interval. So we start from the smallest intervals that only have length 1, so they contain a single element, C11, C22, C33, and so on. And then we keep increasing this to intervals that contain 2 elements. So for example, C45 or C23 and so on. And then we iterate across, throughout increasing lengths of intervals. So let's see how this looks like. So we start basically from length equal to 1. So this is what the following for loop will do. We iterate over all the possible lengths, and the possible lengths that we have to consider are 1 through n. And once we have fixed our length, the length of the interval of keys that we're interested in, we have to define the starting point of the interval, our I. And we do this again from left to right. So we let I iterate from 1 to n minus L plus 1. And then once I have fixed the starting position and I have fixed the length, I know exactly what J will be. So if I have done this, I can set J equal I plus L minus 1. So for example, at some point we set the length of the interval to 2. So we start from I equal 1 to n minus 2 plus 1. Makes sense, n minus 2 plus 1. So we have n minus 1. Exactly, so the last possible starting point of an interval of length 2 is n minus 1, because it will contain n minus 1 and n. And once you have fixed I, for example, to let's say 3, then J will be equal to 3 plus 2 minus 1, meaning plus 1, and will be equal to 4. And this will be an interval from 3 to 4. And this is how we do it. So we always fix a length of the interval, and we iterate over all possible starting points of intervals of that length. And then given the starting point and the length, we know exactly where the end point of this array will be, of this index range. So now we know which CIs we are computing and in what order. So let's try to fill in the values. So we are interested in Cij. This is our final goal. This is the cost of the optimal score for now for a specific subproblem. Initially, we don't really know what it will be, so we try to initialize it to the best or to the largest possible value, infinity. For Wij, we know exactly how to compute it at this point. So if I want to compute Wij, instead of now summing up all the values from I to j, according to the definition of W, I only have to look at the previous value. I only have to look at Wij minus 1. So all the values from I to j minus 1. And then I only have to add sort of the elements for position j, which will be plus pj plus qj. And you can see that now to compute Wij, I only have these two additions. So I always take the one that I computed previously and only add pj and qj. This is why this is much easier instead of just applying the definition of Wij and summing up all the p's from I through j and all the q's from I minus 1 through j. But this is just sort of a helper structure for us, this W. More interesting is Cij. So Cij, to compute Cij, we have to now, after having fixed the length, the starting position of the interval and the ending position of the interval, we said we have to try all possible roots among these elements. And this is what we're doing, what we do in this for loop. So for r equal I to j. So I'm trying all the elements from I to j as a possible root. And once I've fixed the root, I know exactly what the cost will be. We have defined this above. It's this one here. So for a fixed root, sorry, no, this is a minimum. It's going to be this here. So when I pick a root r, then this is the cost, and I take the minimum over all those. So in this loop, I will compute the cost of the optimal subtree containing elements I through j that uses root r. And we said before that the value will be equal to C. Oh no, no, it's not a. It's an entry in our matrix, Ci r minus 1. Plus C r plus 1. R plus 1 to j plus Wij. So this is just plugging in the definition, not the definition, the formula for computing Cij given root r. And then once we have computed that score for that particular root, we will only have to check if that gives us a better solution for this for a tree from I to j. So if t is now better than what we have already computed. So if I've had this problem for a long time, but somehow in this class there's always some problem. So if t, so if that t is smaller than Cij, try to draw this quickly like this, I don't know if this helps. So if this new t that we have computed for this current root r is better than what we have seen so far, we will just remember this as our current best solution. So Cij will be equal to r. Sorry, t. So I mean the value that we computed is t, not r. right? So Cij is equal to T. And we have to keep track of the root, and we do this in this matrix root. So we say that root of Ij is equal to R. Shouldn't be further in. There shouldn't be any intention here. There is one for loop, another for loop, and an if. Yeah. And then when we're done, we return basically what we have computed, namely C and the root. And we'll see that we need the root also. So once this is done, we iterated over all intervals over all length. And we just return C and root, the two tables. Does this make sense to everyone? So again, this loop here goes over all length intervals. This goes from all starting points, and then J is fixed to a certain endpoint or right endpoint of this interval. We initialize Cij initially to infinity. Then we iterate over all possible routes between I and J, compute the cost recursively based on the equation that we described before. So we compute T, the optimal cost of a tree from I containing I through J with root R. And if that's better than what we've seen so far, we remember it. So we remember the best score that we have seen as Cij. And we also remember that root that we have picked in that particular element. So once this for loop is terminating, we have seen all roots, and then Cij will contain the minimum over all possible roots. And for that particular minimum, we have recorded in this table the corresponding root that we have picked. So this is the entire algorithm. Any questions about the description before we go through an example? So what's the running time? The easy part to see is, yeah, what would you say is the running time of this algorithm? You know by now that you always have to look for these for loops, right? You have in this case 3 nested for loops, this one, and this one. And they range maximally from 1 through n. So we have something like n to the power of 3, cubic running time, so order of n to the power of 3. We can also show that it's actually also omega of n to the power of 3, so it's really theta of n to the power of 3. We're not going to go through this. And in fact, using additional insights that we will not use or that we not describe in this class, we can actually get it down to theta of n squared. So the obvious thing to see is that it's a big O of n to the power of 3. And with some additional insights, you can get it down to theta of n squared. So what's clear is that it's big O of n squared. Sorry, n to the power of 3. And with additional insights, we can get it down to theta n squared. Okay. Then let's do one quick example. Not quick, but one small example, I should say, how this algorithm works for a particular instance of p and I values. So let's say we are given 5 keys, k1 through k5. And we need to, so the input to the algorithm are the p values and the q values, so the probabilities of certain keys and of certain dummy nodes. And let's say that we're given this information in this following table, where we have Z values We are recording P, I, and Q. It's a bit difficult. But to make it a bit smaller, I don't know if this helps. So we will have 5 P values. We don't have P0. So we only have probabilities of our 5 keys, 1 through 5, and they are given as follows. We have 0.05, 0.1, 0.05, 0.1, and 0.2. And the Q values then go from 0 to N. So we have Q0 equal to 0.05, Q1 0.10, 0.05, 0.05, 0.05, and 0.10. And we said all these values have to sum up to 1. 2, 3, 4, 5, 6. And yeah, so we have all these values that sum up to 1. And we keep 3 different tables. We keep a table for C, for W, and for the root. So let's see how this looks like. We have C. And now we have this sort of asymmetric ranges of indices. The left range I goes from always 1 through n plus 1. N is 5 for us, so it goes from 1 through 6. So we have values 1, 2, 3, 4, 5, and 6. And the second index always goes from 0 to n. So in our case, from 0 to 5, 0, 1, 0, 1, 2, 3, 4, 5. And we have the same for W. So let me just copy this. I think it's easier. It would be W. And the root looks a bit different. The root goes from 1 through 5. So we don't have these boundary cases for the root. The root goes from 1 through 5. Both dimensions, 1, 2, 3. Okay, so that's what we need to compute. Now, if you look at the algorithm, the first part of the algorithm is really initialization. This is this part. We have to set all these C values, I minus 1 to Q I minus 1. So how does this look in this matrix? How can we do that? These will be all entries that you can see on this diagonal. Here we have C10, here we have C21, C32, C43, and so on. And we just plug in the values for Q. This is our initialization. So that means we will have 0.05 here. We will have 0.10 here, 0.05 here, 0.05, 0.05, and 0.10. So these are our initializations of C and W. We do the exact same thing. If you look at the initialization, we really do the exact same thing. We fill in the same values here at the entry and at the diagonal, 0.05, 0.10, 0.05, 0.05, 0.05, 0.10. Okay. These entries that you can see here these entries here at the bottom of this matrix, those then don't exist for us. because these are entries that look like C31. So I minus 2, I minus 3, I minus 4, those don't exist. We only do this reverse thing once when they're sort of consecutive, I minus 1, but we don't go any further. So these entries don't exist. We don't have to fill in these entries in our metrics. Same for the root. And let's keep the root for later. And now let's try to fill in sort of the entries, just playing sort of the first iteration of this algorithm. So just doing this for the first iteration where we have interval length 1, we pick I equal 1, the first element, and we end at also element 1. So look at the range 1, 1. This is what we're gonna do in the first iteration of this algorithm after initialization. So for so what we have to compute now is C11, which is this entry here. And C11 will be computed according to this algorithm. Yeah, so according to this algorithm, actually to compute C11, we first have to compute W11. You can see this here. So before going down to the C, we really have to compute W first. Okay, so for now we have fixed I equal 1 and J equal 1. And now to compute W11, we have to compute basically W10 and add P0 and Q. No, sorry. We have to look at W10 and we have to add P1 and Q1. Right? I'm just plugging here I equal 1 and J equal 1. So let's see what that means for W11, this entry here. I said I have to look at W10, which is this value, 0.05. And I have to add P1, which is this one here, 0.15. And I have to add Q1, which is 0.1. So the three together should be 0.3. Okay, so the first entry here in W in this first iteration of the algorithm will be set to 0.3. So once we have computed W, now we can check all our roots and compute always the T value. In this case, we only have, in range 1 through 1, we only have one root that we can pick, namely 1. So let's do this. We pick root 1, and then we compute T. And how do we compute T? We compute it according to this. So for the root being equal to 1, and I being equal to 1, and J being equal to 1, to compute Cij, I only have to compute Ci0. I have to look at Ci0. I have to look at C21, and I have to look at W11. Right? I'm just plugging in again these values for Ij and 1. So C10 is what we get here. This is 0.05. Then we have here C21. What is C21? C21 is 0.1. And we have to add Wij, meaning W11, which we just computed, which is 0.3. And if we sum those up, then we should get 0.45. So this was the first iteration, and now we would basically check all the roots and pick the best one. In this case, we only had one root, so this is the best one, and we can fill in this. And we know also, and once we have found the best root, we also record that root in our root matrix or root table. So for range 1, 1, we have picked root 1 to get the optimal tree, which is why we fill a 1 here in this matrix. So the entry with row index 1 and column index 1 will be also 1, because one of them was the optimal root in this range. So this is one iteration. This is what we do for every iteration. And the iterations would just scan this matrix diagonally. So we would continue walking along that direction, and then we would increase the length, and we would always continue along these diagonals until we reach this entry C15, the value that we're actually interested in. And if you would do that, I'm not going to go through all of this. So here you would continue filling the matrix in this direction, and you would end up with a value of 2.75. So this would be the optimal score. This is C15. And the roots that you would have recorded for all your choices that you made are the following. So I'm going to just write it in this matrix. So we have 1, 1, 2, 2, 2. And we have 2, 2, 2, 4, 3, 4, 5, 4, 5, and 5. And again, as before, those are not really relevant to us. So this is what you would get running this algorithm and running along these diagonals. The only thing left now is once you have computed, you know the cost of your optimal binary search tree that contains elements 1 through 5, given these probabilities P and Q. The optimal score is 2.75. Now the question is, how does the tree look like? So can you reconstruct the tree from this information that we have collected here? The necessary information that we have collected are all within this root matrix. So now we're going to basically this example and try to reconstruct the tree that has cost 2.75. How do we do that? It's very intuitive. So we're interested initially in the optimal tree containing elements 1 through 5. Right? So I look up what the root will be. What is the root for the optimal search tree containing elements 1 through 5? So I look up entry row 1 and column 5, and I see that the entry is 2 here. So that means that the root of the overall tree has to be 2. So I can already, let's take like here. I will take K2 as the root, and then I'll do something to the left and to the right. Now to the left, there's only one element. There's only K1, so there's not much flexibility that I have. I can look up everything in the roots, in this root matrix, but I know this will be K1, and I know that there will be 2 dummy nodes, so that's less interesting. To the right of K2 will be elements 3, 4, 5. So I have to look up what the root will be of the optimal tree containing elements 3, 4, and 5. I do this by looking up this matrix in row 3 and column 5, and I see that the root must be 5. So the optimal root of the subtree is 5, and therefore I can add K5 here. Again, to the right, there is nothing of K5. This is our maximum key, so to the right, we only have the dummy node. So what's left now is what's happening to the left of K5, which is also to the right of K2. So now we have basically left 2 elements, namely elements 3 and 4. And again, I look up what the root will be in the optimal tree containing elements 3 to 4. So I look up row 3 and column 4, and I see that the optimal root must be 4. So to the left of K5 will be K4. And then we're done. There's only one key left. So there's nothing, of course, between K4 and K5. And to the left will be K3. And the rest, of course, we fill with dummy nodes. And the cost should be, I'm not going to verify this now, but if you plug in just now the definition of the cost of such a tree, using these P and Q values, you should get a value of 2.75. So I'm just claiming this here. I'm not going to calculate it. But the cost of this tree should be 2.75. Which is exactly the value that we see here in the upper right element or entry in this matrix, 2.75. Okay. Any questions about that? This is how do you compute an optimal search tree by using dynamic programming. Then I want to go through one more example, the last one, which will be much shorter than what we've seen so far, much simpler. Just to also wrap up basically what you have done before. You looked at the problem of computing shortest paths. And I want to revisit this problem with a different variation. We are trying to compute all pairs shortest paths. So what you have done, I believe, in the first part of the class, is you have looked at the shortest path problem for a single source. So you always, if you run Bellman-Ford, you will get the shortest path for one vertex to all other vertices. And now we're interested in computing all pairs shortest path. Of course, you could use Bellman-Ford and run Bellman-Ford on every single vertex, and then you would get by this procedure all pairs shortest paths. But this would give you a cost of the number of nodes times Bellman-Ford, and Bellman-Ford is number of nodes times number of edges. So you would end up with a running time of something like number of nodes squared times the number of edges, which might be inefficient if E, the number of edges, is large, if it's in the order of V squared. And that's why we want to do this a bit differently today. And I want to show you a very simple and intuitive dynamic program that you can explain essentially with one figure, how you can do this faster without this dependence on the number of edges in your graph. So this is the last example using dynamic programming. So this is going to be the final example. All pairs shortest paths. And we are given a directed graph, a weighted directed graph G using our traditional notation. And we assume that we don't have any negative weight cycles. So with no negative weight cycles. The question is how to compute shortest path UV from U to V for all U and V in V. And I said you could use Bellman-Ford, as you have done, and just run it on every single vertex. And this would give you an overall running time of big O of, so Bellman-Ford on every vertex, I should say. Then the total running time would be big O of number of, write this with my pen. It will be something like big O of the number of vertices squared times the number of edges. So what we try here is to use a dynamic program. And you will see that it can be done more efficiently than this. And so the critical insight is really, so how do we define a subproblem? If you want to compute the shortest path between two vertices, what could we come up with? What kind of subproblem could we define such that we can relate the shortest path to shortest path of certain subproblems? So it's useful to think about an extreme case of which vertices you allow to use as intermediate vertices between U and V on the shortest path. Because the shortest path from U to V will contain some of the other vertices as intermediate vertices. But what happens if you don't allow anything? So if you say that the shortest path from U to V that is not allowed to use any other vertex in your graph, that would be just an edge, right? So you only have the chance to use a direct edge from U to V if you're not allowed to use any intermediate vertices. And then you could say, and then you could start asking, well, what if I sort of gradually try to increase the set of vertices that I'm allowed to use as intermediate vertices? How can I relate the shortest path that is allowed to use certain intermediate vertices to the shortest path that is only allowed to use a subset of these vertices as intermediate vertices? And this is what we're trying to formalize. So let's say that we have, I think I write this. So we have our set of vertices, and now we number these vertices arbitrarily from 1 through n. And we consider two vertices I and j in V. And then we define the distance from I to j 0. Oh, sorry, I think it's more general first. Call this k minus 1. So the distance ij k minus 1 will now define the length of the shortest path from I to j that is allowed to use only the vertices from 1 through k minus 1. So the first k minus 1 vertices, according to the numbering of my vertices. Okay, so when you write this down, distance of ij k minus 1 denotes the length of the shortest path from I to j, which can only use the nodes basically from 1 through k minus 1. Intermediates. And so the extreme case in this case would be distance from I to j 0, which would simply mean that we're not allowed to use any intermediate vertex, and we have to take only the edge, the direct edge from I to j. So this is the length of the edge, Lij, if it exists, and infinity otherwise. So is the definition clear to everyone what distance ij means? Distance ij k minus 1, shortest path from I to j, using only vertices from 1 through k minus 1. And so if you set this to 0, we're not allowed to use any intermediate vertex, and then it's just the length of the direct edge. And now comes sort of the central picture that tells everything about the algorithm. So let's say you have computed. Let's say you have computed the optimal for the shortest path, the length of the shortest path from I to j, using vertices k minus 1. It will look like this. So this has length distance ij k minus 1. And the question is, so this is the shortest path using only vertices 1 through k minus 1. And now the question is, what happens if you gradually expand the set of intermediate vertices that you're allowed to use? So if you now go to vertices 1 through k, you're in principle allowed to use this additional vertex k compared to previous iterations. And let's draw this here. So we have this vertex k. And then the shortest path from I to j that uses vertex k will look somehow like this. You have some path that goes from I to k, and you have some path that goes from k to j. Right? So this is the shortest path from I to j that uses k. So we're computing shortest path. That means we don't introduce any cycles in our path. We compute a simple path because otherwise, because we don't have negative cycles, otherwise we could cut out the cycle and shorten this path. And that means that this node k will be visited only once, and that this node k will not occur on this path, and it will not occur anywhere in this path. So let me call these P1 and P2. This path P1 and this is subpath P2. So we know two things about P1 and P2. We know that P1 is optimal from I to k because of optimal substructure. We argued about this before, that the optimal or the shortest path between two nodes contains within it shortest paths again. So P1 and P2 will be shortest. And we also know that k will not be in P1 and k will also not be in P2. Right? So we know that k is not in P1 and it's also not in P2. And we also know that this path, P1, will only contain, since it doesn't contain k, it will only contain vertices 1 through k minus 1. Right? This is how we computed it. We said that this path here on top is the shortest path using the first k vertices. So removing k, there's only k, the vertices from 1 through k minus 1. Right, so along here, I have vertices from 1 through k minus 1. And along this path, I only have vertices from among 1 k minus 1. And that means that the length of this path, can someone tell me what the length of this path will be then? In terms of this notation. So will this be simply the distance from I through k using the first k minus 1 vertices, right? So it has to be optimal. It doesn't contain k, and it contains only vertices from 1 through k minus 1. And this is what we defined as the length of the shortest path from 1 through k with k minus 1 parameter. And the same is true here. So this has the length distance from k to j, again using only vertices from 1 through k minus 1. And that's it. This is the only thing I need to know. Once I'm including this extra vertex k, I compute the shortest path that includes k. I know that I have computed the subpath before as distance ik k minus 1 and distance kj k minus 1. And so I only have to add them up to get the length of the upper path, and I compare it to the lower path, and whatever is shorter is my optimal solution. My optimal path using the first k vertices. So I know how long this path is because I have computed it before when I set this parameter to k minus 1. And now by simply adding up this term and this term, I know how long this path will be. I've computed these ones before because these again use smaller parameters k minus 1. And whatever smaller is sort of my optimal path from I to j that uses vertices from within 1 and k. Let me just write it down and it should get clear. So we know that we can use k, or using k gives us a better shorter path if the following holds. So using k is better if the distance, so basically summing up this new path that contains vertex k, is smaller than the distance than our previous path. So distance ik k minus 1 plus distance from k to j k minus 1. If this is smaller than the distance from I to j using k minus 1. So on the left-hand side, this part here, this is the shortest path that uses k. And this is the shortest path that doesn't use k, and you just take whatever smaller. And this is your shortest path that uses anything from 1 through k. So putting it all together, this gives us an algorithm that is called the Floyd Warshall algorithm. This Floyd Warshall, which gets as input directed weighted graph and weights or length, edge length L. So we have to initialize all the edges or these distances to our edge weights if we don't allow any intermediate vertices. So this is just 2 for loops where I first go over all pairs of vertices. So I 1 through n and j 1 through n. I set the distance from I to j to infinity. And then I check which edges exist, and those I set to the length of the edge. Now, after doing this, I again go over all edges in my graph, so all ij and e. And I initialize the distance from ij using no other intermediate vertex, simply to the length of this edge, Lij. So this is just the initialization. It's not very interesting. The more interesting part is coming now. Now we're sort of gradually increasing the set of vertices that we're allowed to use as intermediate vertices. So before we said we don't use anything. In this for loop, we will start by allowing 1, the first vertex, and increase this all the way up to n, using all the vertices. So k is going from 1 through n. And then again, we check all our pairs of vertices as before. So for I equal 1 through n, and for j equal 1 through n. I simply compute the distance from I to j, where we are allowed to use vertices 1 through k, as the minimum of the 2 elements that we have computed for. So it's either the distance from I to k, k minus 1. This is the exact same thing that I've written before, plus distance from k to j, using only k minus 1. And the second is distance from I to j, using k minus 1. And that's it. That's the entire algorithm. This is how we compute all pairs shortest path. So we start by not allowing any vertex as intermediate vertices. Then we know the shortest path between all pairs is simply the direct edge. And if this edge doesn't exist, then I set it to infinity. That's what I do in this first for loop. First, I set everything to infinity. And if there is an edge, I just set it to the length of the edge. And then I gradually expand the set of vertices that I'm allowed to use as intermediate vertex. I start with k equal 1, and I go through all pairs, and I always check if sort of including this extra vertex here in the upper line here gives a shorter path than the optimal path that does not include this extra vertex. And whatever is smaller, I take as my distance ijk. And I keep on doing this until I have reached n. So k equal n means I'm allowed now to use all vertices in my graph as intermediate vertices, and then what I really get in the end is the shortest path from I to j. This is the whole trick. The running time, is this now better? So we said we wanted to be better than Bellman-Ford. Bellman-Ford was v squared times e. What is the running time of this algorithm? Any suggestions? You look at that description. What's the running time of Floyd Warshall? Yeah, it's n cubed, exactly, because we have these 3 nested for loops, and each loop here has index range n, meaning number of vertices. So this here will be big O of number of vertices cubed. And the initialization is just considering all pairs of vertices. So this is going to be order v squared. And this is better than, so v squared is better than v squared e, especially if e is large, and because e can be in the order of v squared. And if it's connected, then e will be at least v minus 1. So in all relevant cases, this is better, or at least as good as running Bellman-Ford for every vertex. Okay, any questions about our last example? This was it for dynamic programming. This was our last example, how we solved, in this case, all pairs shortest path using dynamic programming. Yeah. In the upper part, you mean? So this one? I don't see where you're pointing, but this the lower part or the top part? The top part, so you go here simply between all pairs of vertices, right? I 1 through n and j 1 through n. Ah, sorry, this for loop has to be outside of this for loop. I don't know if this is clear. 1 second. Maybe this is the problem here. So this one here, I can do that. Almost. So this has to be out here. Maybe that was your question. Because you first go over all pairs of vertices, no matter whether there's an edge or not. So you say, okay, here will cost infinity. And then you actually check which edges exist. And for those pairs of vertices where there is an edge, you actually update this distance to the actual length of the edge. Such that after this first part here, whenever there's an edge, distance of ij0 will be the length of this edge. And when there's no edge, the distance will be initialized to infinity. Okay? Then yeah, too many. Way too many. Okay. So then I want to start a new topic, and I will, in this last two lectures, basically start two new topics. So, and this is just for the sort of to show you that this stuff exists. So this first part will be linear programming, which is another very powerful algorithmic tool. We won't go into any details of how to solve linear programs. There's a lot of sophisticated algorithms, a lot of theory that we will not deal, that we will not cover in this class. But I want you to have heard at least that it exists and to roughly know what it is about and how it can be useful. And then in the last part of the lecture, I just want to give sort of a survey of what distinguishes easy from hard problems, such that you have heard of things like NP completeness at least once. So and I will probably do these two lectures now on slides, because I think for this, it's nice to have lots of visualization. This is the very nice thing about linear programming. You can explain a lot of algorithmic ideas in nice two-dimensional pictures to get a very rough idea of what the algorithms and the methods do. So I'll use slides for this, and I'll see how it goes. I'm actually happy. I would be very happy to get your feedback. I think you can fill in. I forgot how it's called, but you must have received an email where you can give a rating to this class. So I'd be very happy to get any feedback, positive or negative. And yeah, tell me what you liked, what you didn't like, what I should change, what I should not change. So any kind of feedback would be very welcome. So in this last part, as I said, I will start with slides. I will just use this 3 minutes to introduce sort of the basic idea of linear programming. And to put it into context first, we have seen a lot of what you would call optimization problems. And optimization problems, if you think of something like shortest path that we have just done, minimum spanning tree of maximum flow computation, or longest increasing subsequence, all these problems are optimization problems in the sense that they are defining a set of feasible solutions using certain types of constraints. A shortest path, for example, requires you to start at S and to end at T, for example, and it has to be a path. Minimum spanning trees, well, you look at all spanning trees, so you are not allowed to introduce any cycles. You're required to span all the vertices in your graph. Max flow, you have constraints that limit you by the capacity, so you're having capacity constraints, and you have flow conservation, and so on. And so once you have formalized or defined the constraints that define feasible solutions to your problem, then you want to find the best one. So you will want to look for the shortest path, you want to look for the minimum spanning tree, or the maximum flow. So in this framework, think of optimization problems. And then once you're looking at linear programming, in linear programming, we also have constraints that will define sort of our feasible solutions, of solutions that we can consider. And among these feasible solutions, we want to find the best one. And both these elements will be defined by linear functions. So both the constraints and the objective, sort of how to measure the quality of your solution, both things will be done using linear functions. And we'll see an example. Linear functions of that type. So you can see that here f of x is a linear function in x. It has multiple variables, in this case, n variables, x1 through xn. And you can see that that this function depends linearly in all these variables. So we have these kind of linear functions to describe the objective and also to describe feasible solutions to our problem. So, but I won't go into more definitions. I wanted to sketch one problem, but I think, yeah, give me 3 minutes. Can I have 3 more minutes? Are you in a rush? And I'll just introduce this one problem to you, which is resource allocation. Resource allocation is supposed to help you with your life. So let's say you have 168 hours that you can spend every week in fun activities or not so much fun activities. In particular, you can choose to spend your hours, the 160 hours that 1 week has, into either studying for the final exam of 465, or you can decide that you're actually not really, that you don't really care and you spend more time in partying and having fun. And everything else could be things like grocery shopping, you have to sleep, you have to eat, and so on. So things that you will need to do to survive. And then we can describe sort of necessary conditions using the following equation. So we can say that to survive, you need to spend at least 56 hours in what I call E, everything else. So you have to spend at least 56 hours in sleeping, in eating, in sort of necessary things, grocery shopping, just to survive. I don't know if this is a realistic number. It might be different for some others, but some people need more or less sleep. But this is sort of our model. We assume that in order to survive, you have to spend at least 56 hours in E activities. Now you also want to pass your 465 class. And let's say in order to do that, you have to spend at least 60 hours in studying for the exams, for the final exam, for the midterm, and for the homework, and for going to classes and so on. So you will have to spend at least 60 hours. And then the third constraint is that you don't want to get crazy. So in order to have a healthy brain, you don't want to only study and eat and sleep, but you also want to have fun in between. And that's what this constraint tells you. It says that P plus E, the time that you spend in partying plus sleeping plus eating, should be at least 70, such that you don't, get crazy. So this is sort of just, the bare minimum. That this is what you would call constraints that describe the bare minimum, such that you survive, that you pass the class, and you don't turn crazy. But on top of that, you have an objective. So you don't find any PES number of hours that satisfy these three constraints. You want to find one that make you most happy. Of course, probably some of you will have different objective values, but overall, let's say studying doesn't contribute to your happiness. And again, this might not be realistic. Let's say only partying and everything else, helps you. And typically partying sort of is more valuable for you than eating or sleeping. And it's why you would sort of give this coefficient 2 to P compared to E. So the way you measure your happiness is by calculating 2 times P plus E. So this is sort of to quantify your happiness. Your happiness should be you should be able to express your happiness using this P and E, 2 times P plus E. And then the question is really, how do you find values, the number of hours for studying, for partying, and for everything else, such that you survive, that you pass the class, that you don't turn crazy, and on top of all this, such that you're as happy as possible. And this is sort of what this linear program will say, but this will continue the next time, unless there's questions. Good, then thank you very much, and see you next week.